So our previous video was somewhat abstract. We sort of really dove into the thick of it with natural transformations and maps between this monoid and that monoid. So I thought in between this and the next episode, we'd maybe get our hands on something a little more tangible. So remember, one of the things that we're working towards is trying to understand. We're trying to prove that if R and S are commutative, and if their module categories are equivalent, then we would like to be able to conclude that R and S are isomorphic as rings. Okay. And as previously mentioned, one of the steps that we're going to take to get there is the general statement that the center of a category, which we described last time, we described it as a commutative monoid. It turns out in the case of modules, it actually has the structure of a ring, and that ring is isomorphic to the center of the ring. So of course, if R is commutative, it will be isomorphic to its own center. And the idea is that a center of a category, this is now a categorical concept, so it should be preserved under equivalences of categories. Great. But so how do we realize this module structure? So I'll say something somewhat abstract in a moment, but then we're going to dive into those technical things in the next episode. We're going to hone in on the case of rings in this episode, rings and categories of our modules. So remember that in general, a center of a category for us, this is supposed to be my version of a fancy C. The center of a category was the endomorphisms of the identity functor on that category, right? Natural transformations from the identity functor to itself under composition. And if we're going to give this a ring, like usually our composition corresponds to some sort of multiplication structure, so there should be an addition on this endomorphism ring. So in particular, there should be an addition operation, since every element of this, it has to give you a map from each object to itself, right? The datum of a natural transformation should consist of a morphism from each object to itself, subject to some conditions, and so that means that if if we've got two of these natural transformations, which is some maps here, then whatever the addition is of these two natural transformations, presumably it could be described at the level of some addition operation which applies to general Hom sets. So in the case of modules, this is certainly the case, right? Like if you have two, so very generally, not even just from an object to itself, but if you have any pair of modules and any pair of morphisms between those modules in some category of modules over some ring R, we can define an addition operation, on these morphisms simply as such, right? Because the modules themselves have an addition operation, right? So this gives us an addition operation. And in fact, this addition operation on any pair, on any Hom set in the category of R modules, this actually makes each of these Hom sets into an abelian group under addition. And so in this case, the sort of fancy term for in any category, if all of your Hom sets have the structure of an abelian group, then we say, a fancy way to say it is that it's enriched in abelian groups. So whenever you see the sentence that says your category is enriched in blank, that means that your Hom sets have the structure of blank. But of course, that's not that's not only it, like it should be compatible with your composition, right? Because obviously we want compatibility of structures, so we should expect this some sort of formula like this to hold. Of course it does in our case. And notice that also this means that we have some notion of zero maps as well, right? So because there needs to be some map that acts as the additive identity on our HOM set structure, and for us that's going to be the zero map in the category of modules. But again, we do eventually want to, the question is, what's sort of driving me in this series is, well, how general can we make these proofs, right? So we're aiming towards giving a ring structure on the center of the category of R modules, but what really is essential here, and it just seems to be this fact that we have an addition operation. So more generally, this idea should apply to the case. So we say that a category C is pre-additive if it's enriched in abelian groups. There's two different ways of saying the same thing, right? And so the less fancy version of that is just saying all of our HOM sets have the structure of an abelian group, and that structure is compatible with compositions of morphisms. Okay, and fantastic. So that's really enough. That's really enough for us to describe, to give the structure of a commutative ring to the center of the category, right? So I mean, we essentially have written out this condition up above, right? So all you need to do is convince yourself that, well, this now gives us a ring structure, and of course it does, right? Because by definition, so if we assume, so maybe I could call this fancy plus. So I'm defining what the additive operation is on our endomorphism set, let's say, of the identity functor. So I'm defining it. I'm supposing that my category is a pre-additive category, so that I have a group operation on the level of morphisms. I'll simply define my operation on natural transformations to be this group operation on the individual components of the corresponding natural transformations. And this satisfies a ring, right? Automatically, well, okay, not automatically, you still should go and check that this satisfies the rules, but we can see pretty clearly from the definition that it will also, the endomorphism, the collection of endomorphisms will inherit an abelian group structure under this operation. And remember our multiplication in here that made this a commutative monoid. Our multiplication was composition, and again we'll see. So if this was, maybe I'll write it like this. Let me make a new line. Let me make a new line down here. So it's got to respect composition. Of course, if we take the composition of these maps, evaluate this whole thing at some object. What is this? Well, this will just be sigma x composed with eta x plus gamma x, but because we're assuming this is an additive category, of course everything distributes. And sure enough, this is exactly what we expect, right? So now, okay, we understand that probably the widest case in which we can apply these things that we're about to say about our the center of our category being a commutative ring is exactly when the underlying category is a pre-additive category enriched in abelian groups. So in the next video, we're going to address the general theory of pre-additive and additive categories and talk about, in my opinion, what are some really cool theorems about them. But now, after several promises that we'll do this, we'll finally hone in on the case of the category of modules. So lemma, well, we can even be more specific. So let R be a ring, any ring. Of course, when I say ring, I mean a ring with identity, not necessarily commutative. And then we're going to define, well, define for each element z in the center of our ring, we're going to define the map. So this will be and each module. We're going to define the map eta zm. So this will be a morphism from a module to itself. How are we going to define it? It will be given, we will take an element and simply act on it by z in the module. So I claim, so this lemma, the point of the lemma is going to come in several minutes. I'm sort of doing a horrendous thing and stating this lemma in the worst part possible, but I kind of want to give explicit definitions on our way to this lemma. Perhaps maybe you can already see where it's going. But this, I claim, will be a module homomorphism. Why is that the case? Well, certainly the additivity, right, for any m plus n, the additivity simply comes from our assumption that m is an R module. And since z is in the center, it's also the case that if we apply this, just using the commutativity, I'm going to drop the dot and just write things beside each other. Simply using the associativity and the commutativity of the module operations, we can see it is in fact a module homomorphism. And, well, moreover, I claim that this map, eta zm, well, rather the whole collection of these maps, I claim that this lies in the center of the category of R modules. Why is that? Well, simply, how do we verify such a thing? Well, we simply need to take an arbitrary module homomorphism, apply the identity functor to it, and then look at eta z as some endomorphism of the identity functor. So this will be eta zm, this will be eta zn, and we simply must verify the commutativity of this diagram. So going around, say, this way first, we have eta zn composed with f of m. Well, eta zm simply has you multiply by z, but f was assumed to be a module homomorphism, so that means we can pull the action inside. And sure enough, this is simply f of eta zm applied to m, and therefore the commuting of this diagram is verified. So it really does land where I say it lands. So we're halfway through the statement of this lemma. And now, so I'm going to, but let me give a name to this map. So I'm going to call this phi. So I have zr phi into the center of my category of R modules, and it's going to send z to the natural transformation eta z. I'm also going to define a map which will be the inverse of this in order to establish an isomorphism. I'm going to call that psi, and I'm going to send a natural transformation to, well, that natural transformation determines a map from the ring itself to itself, and evaluate that at 1. But I must convince you that this really does lie in the center of this ring. How should I do such a thing? Did I put it in my notes? Probably not. Probably not. Or perhaps it is. Well, we do know this. So our eta r. We do know that this is a morphism, a module morphism from R to R. And so that means in particular that every, so eta R evaluated at some arbitrary R, well, this is eta R evaluated at R, that's simply the action map. And since this is a module homomorphism, we can pull the action of R out in front. And so what do we find? Well, it turns out that this map must simply be given by a right multiplication of some element of R, right? Eta sub R at 1 is just some element of R, so it's going to be given by right multiplication by an element of R. So, okay, at least we know that this is in the ring. Why is it in the center? Well, we're going to rely on the fact that eta is a natural transformation of the identity functor, right? So we could take multiplication by an arbitrary element of R on the right. This will determine a left module homomorphism. And then, again, apply the identity functor and the fact that eta is a natural transformation thereof. And, well, we know that this diagram commutes, right? We know that this diagram commutes. So what does that mean? That means if I went, well, S dot R, and then I applied eta R, this should be the same as if I went the other way, as if I went eta R S, and then multiplied on the right by R. Now, this is a module homomorphism, so I can pull everything out in front here, and I can pull everything. I can pull the S out in front on this side, and I know that this has to hold for all S, right? This holds for all S in R, and so therefore this must be true when S is equal to 1. So in particular, R eta R1 must be epsilon R1 times R, but R could also be chosen arbitrarily, right? Every single element of the ring, by taking it as right multiplication, that determines a left module homomorphism. And so therefore these multiplications must commute by the arbitrary choice of R. Eta 1 R actually is in the center. So I've given you the absolute worst way to state a lemma you've probably seen in your entire life. But the punchline is that both phi and psi, these determine a mutually inverse pair of ring homomorphisms, which is to say, these are the explicit pair of morphisms which realize, or an explicit pair of morphisms which realize the center of your ring is isomorphic to the center of the category. So what do we need to do? We need to verify that these are in fact ring homomorphisms, and we should also verify that they're mutually inverse to each other. So we have a map from CR to the center of our R module category. That's phi. Z goes to phi z. Well, why is this a ring homomorphism, well, we simply need to check additivity, multiplicativity, and the fact that it preserves the unit. So, well, let's see, psi of z plus w. Well, we can check this. We can check what this map does on the level of any object in our category. And so therefore, we might evaluate it at any element of that module. So what is this? This will be eta of z plus w m applied to little m. But this is z plus w acting on little m. And of course, by our module, by the fact we're assuming this is an R module, this is z acting on m plus w acting on m, which is, of course, eta z acting on m, or evaluated at m, eta w m acting on m. And what is that? That is, of course, phi of z at m acting on m plus phi at w m acting on little m. And so we can conclude, hence phi. We've checked it on every test object, so phi of z is phi of z plus. Maybe if I wanted to be really careful with which addition operation I'm using here, I'd write it as this plus. But I'm going to be sloppy and fast and loose with that. Okay. Great. So that condition satisfied. Of course, we can check that our multiplication is satisfied. But again, a pretty just straightforward computation. Maybe I'll leave this for you. I'm gonna leave the rest of those verifications to you. Like usual, yell at me in the comments section if you would prefer to have detailed proofs, complete the proof for you that phi is a ring homomorphism, that psi is a ring homomorphism. So we need to check the multiplicative condition and the fact that it preserves the identity, multiplicative identity. Great. Okay. So the other thing that we must verify now is, of course, that these maps are mutually inverse to each other. So going through that, well, we have psi composed with phi applied to z, and we need to check that we get back z. Well, what psi does is it says, well, this thing is a natural transformation. I'm going to take whatever that natural transformation is, look at the corresponding map at R, and I'm going to evaluate that at 1. But that natural transformation is eta z at R, evaluated at 1, and that is simply multiplication by z. And so, yes, indeed, we find that we recover z. Okay, the converse takes slightly more work to establish. So let's let M be an R module. And we're going to take some little m in big M. And so now we define f sub m to be a morphism from R into M. By, how is it going to be defined? So fm applied to R is going to be defined by simply taking M and applying R. So I claim, and you can verify this for yourself, always have to remind you to yell at me in the comments if this upsets you or you get stuck. This is an R module homomorphism from R into M. And so, well, what we're going to do is now, again, apply the, so what am I trying to show? Maybe I should say that. So let's be clear. So I want to show that phi composed with psi applied to eta, or sorry, I keep saying eta, I mean epsilon. Applied to epsilon is equal to epsilon as a natural transformation. And it should be enough for me to, again, using this similar trick. Well, we can simply test it if we test it at an arbitrary object, M, and evaluate that at an arbitrary point in that module, that should be good enough. So this is the statement that we're after ultimately. So with that in mind, we've picked our arbitrary M, we've picked an arbitrary point in M, and now I'm going to, and we've defined this module homomorphism. So again, I apply the identity functor, and I use the fact that I have a natural transformation of the identity functor. Hence, I should get a commuting diagram, where down here I'll have epsilon r, and over here I'll have epsilon m. Fantastic. And what do we get from here? Well, we know that this diagram has to commute for all elements of R, right? So that means that we have that epsilon m of f m of R must be equal to epsilon R. Have I written things in a strange manner? No, it's okay. This must be the same as applying Fm to epsilon R at R. I think I probably want to evaluate things at 1 here somewhere. Okay, so what is this? This is going to be epsilon m at r dot m. And over here, I'm going to have epsilon r at r dot m. Okay. And how does that help me? How does that help me? So in particular, this does have to hold for all R and R. So as I suggested, we can take this to be, if we plug in R equals 1, we should find that epsilon m at m is simply equal to epsilon R evaluated at 1 dot m. So we can already see the hints here that this is just giving back the result that we want. So I suppose let's take a look now at this actual composition. So we have psi, phi composed with psi at epsilon, and evaluating this at m. What is that going to be? Well, the phi says that this has to be eta of psi epsilon at m applied to m. So that is going to be psi epsilon, which is an element of the center of our ring, acting on little m. But psi epsilon is defined to be epsilon r at 1, and of course that's acting on m. And then the thing that we just demonstrated was in fact that this is epsilon sub m at m. And so therefore, the right-hand side is equal to the left-hand side, exactly as we wanted above, and therefore these maps are, in fact, mutually inverse to each other. Okay, so that is the, at least we now have an explicit understanding of how the centers for an arbitrary ring, how the center of the ring is isomorphic with explicit isomorphisms to the center our category. But now that we've seen the specific case, I mean, this is the thing that we're ultimately interested in. But again, we have this understanding that, well, what was really essential here to have the ring structure? What was really essential here is just the fact that we have an additive category. So, of course, we do want to, we also have already that if I have two categories, C and D, that if those categories are equivalent, then the centers of those categories will be isomorphic as commutative monoids. We would now like to know, though, those maps that we wrote down previously. In the event that these commutative monoids have the structure of commutative rings, in particular in the case when C and D are pre-additive categories, we would like to know that those exact morphisms we wrote down continue to be ring isomorphisms. And so in the next episode, we're going to develop some of the general theory of additive and pre-additive categories and establish this from a sort of higher point of view. So now you're armed with a bunch more tools to go and prove some theorems